Okay, so moving on to chapter 7, question 40. What we're basically asking for all of these little sub-questions is, do these following compounds have delocalized electrons? And some of these are going to be neutral, some of them are positively charged, and I think even some of these are negatively charged too. Um, Not for question 40, but later on we'll also have negative charges that we have to move around. So just like we were talking about before with, being able to use reagents going forward and as well as going backwards, you need to be able to identify when electrons can be delocalized for neutral compounds, for positive compounds, and for compounds with a negative charge on them. So you can have delocalized electrons for all of these potential situations. So let's just look at sub-question A. So this is a neutral compound. Thinking about some of the rules that we set for delocalized electrons. So one, we can only really move pi electrons or lone pair electrons. So here it might be good for all of these to go ahead and draw in lone pairs for whenever you get a chance, just so we can have something to play around with later. Um, so another thing to keep in mind is that these electrons aren't going to be able to skip over sp3 hybridized carbon. So if you get tempted to do that, just remember that you can't skip over sp3 hybridized carbon. So first things first, let's try to identify a couple of pi electrons. We've got some pi electrons right here, and we've got some lone pairs. I'll just abbreviate them as LP right here. So I think you can either play around with trying to move around a lone pair or a pi electron. For me, I always find pi electrons easier to move around, just to start off with. So let's go ahead and play around with that possibility. So we've got this pi electron right here, or pi electrons. We can move these to this adjacent bond right there. And so to prevent us from breaking the octet rule for this carbon right here, we have to then move these electrons within the carbon-oxygen bond. And we can't move them over here because then that would break the octet rule here. And so the only other place we can potentially move them is onto this oxygen. Okay, so we can move them up to the oxygen, and we can draw, a resonance form of this, of this ketone, like so. We can add 1, 2, 3. And so this double bond right here used to be the single bond right here, and now we have this oxygen up above with 1, 2, 3 lone pairs now instead of just 2, and we can't forget that last CH3. Okay, so then also what we'll have to do now is do a charge calculation. So if you look at this oxygen, it's going to be 6 minus 246, which is 0, and then we'll subtract another, another 1 from this covalent bond. So this oxygen is going to end up being negatively charged. So that must mean that we have to have a positive charge somewhere else in the molecule. So we've got this carbon right here that lost some electrons. So we might want to start calculating charges over in this general area. So once we start mucking around with bonds being broken or made, that's where you should really focus in on to see where you might have a positive or a negative. So let's think about the number of hydrogens on this carbon on the end. So we started off with 2 hydrogens. We know that because it was neutral to begin with, and overall we have to have 1, 2, 3, 4 bonds on this carbon to have it be neutral. So at the end we have 2 hydrogens still attached. So if we did a formal, formal charge calculation on this carbon, we'd have 4 minus 3. So that's going to end up being carbon as positive 1. Okay. So whenever you're doing these kind of calculations, you have to remember to always double check your charges, make sure everything looks good. Okay. All right, next one here. We have this carbocation and we have a pi bond. So remember again, we can only move pi's, and we can't ever formally move a positive bond or a positive charge directly. The positive charge can be moved around because of the way that we move lone pairs around, but it never moves directly. Okay, so remember also here we can never really skip over sp3 carbons. So thinking about this carbon in the middle, this carbon has 2 hydrogens coming off of it, and it's going to be sp3 hybridized. So some people get very tempted to do this kind of thing, where you take this lone pair and you move it on to the next bond. But if you do that, again, we'll end up having this kind of situation where we have a Texas carbon or a carbon with 1, 2, 3, 4, 5 bonds on it. Breaking the octet rule, it's going to be impossible to do this. Okay, so can't do that. Um, and although you could potentially draw a kind of situation where you drew this kind of delocalization, where you have this lone or this pi bond going over to this carbon right here, we could technically do that. So we would get still the same number of carbons positive here, and we'd end up getting a positive on this carbon 2. And overall, we have to remember to write out our lone pairs. So carbon 1 had 2 hydrogens on it, and what we're saying with this arrow is we're taking the electrons in this in this pi bond, and we're pushing them over onto carbon 1 to act as a lone pair. So that means they must show up like this, which means that this carbon 1, has to have a negative charge on it. If we do your formal charge calculation again, it's 4 minus 1, 2, 3, 4, 5. So this 4 minus 5 is negative 1. Okay, so technically this is not incorrect, but this is going to be a very unstable structure. Having multiple charges on the same molecule is never a very energy minimum, or a very good energy minimum. So I would always try to avoid putting multiple charges on a single molecule if you can help it. Okay. So overall, this molecule does technically have a delocalized electrons in this way, but one thing they were trying to have you, or trick you, is they were trying to make you say that you could actually put these pi bond or these pi electrons onto this carbon-carbon bond right here, and that can't happen. Okay, so moving on to sub-question E, we've got a totally different situation now where we have, let's say, carbon 1, 2, and 3. It's a similar situation to what we had up in sub-question C, but in this case, if we try to actually move the pi bond over to this 2 to 3 carbon bond, we're not actually going to be skipping over any sp3 hybridized carbons. So that's actually a very valid way of drawing this out. So I'm just going to redraw this carbon 1 and carbon 2 to make it easier to play with. And so we can actually go ahead and take these pi bonds, or pi electrons, and move them over to this 2 to 3 carbon bond. Again, this is sp2 hybridized, carbon 2 is sp2 hybridized, carbon 3 is sp2 hybridized. So there's no big deal here. So we can draw a resonance form, delocalize this pi electron system. We can redraw this 5-membered ring like this. And so now we've got carbon 1, 2, and 3. One thing to remember now is that you have a positive on the left, you must have a positive on the right. Carbon 1 started off with 1 hydrogen. Carbon 1 also has 1 hydrogen in the resonance contributor on the right. And so that must mean carbon 1 is positively charged. Again, you can do the formal charge calculation, 4 minus 3. It's going to be positive 1. Okay? It's very, very important for you to remember to draw out the charges for these guys. Okay, so sub-question I, you can potentially draw out a delocalized electrons for this molecule because you have 2 pi bonds adjacent to each other. So if you look at carbons 1, 2, 3, and 4, all 4 of these carbons are sp2, 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 sp2. So we're going to have these p orbitals that are all facing in the same direction. You can delocalize electrons throughout all of these guys. Okay, so one way you could potentially draw a resonance form of this 6-membered ring is like so. Okay, so you can redraw where these pi electrons are going to sit. So we'll redraw the 6-membered ring like this. And so we could potentially have this pi bond broken and reformed on the 2 to 3 bond. And if we do that, we can't actually draw, or we can't actually leave this molecule as it is, because going back again to the whole octet rule, Texas carbons, we can't have this kind of configuration. Okay, so to prevent this kind of 1, 2, 3, 4, 5 bond, 5 covalent bond configuration, or Texas carbon configuration to carbon 3, we have to remember to always break this other bond. Okay, so let's go ahead and get rid of this bond and put it up here as a lone pair. So now what we have, we still have this hydrogen on carbon 4, but in this case we're not actually breaking the octet rule. Okay, so 2, 4, 6, 8 electrons total are surrounding carbon 4. So that's totally fine. The only thing we need to remember to do now is to calculate formal charge. Again, carbon 1 started off with only 1 hydrogen, so at the end of the day, carbon 1 is going to have 4 minus 1, 2, 3 bonds, so that's going to be positive. Okay, so if we have a positive, we must have a negative. And so at this point in your OChem career, it should be obvious that carbon 4, since it has a lone pair and 3 bonds, it's going to be negative. But again, if it's not, go through the formal charge calculation again. It's going to be valence of 4 for carbon 4 minus 1 lone pair, so 4 minus 2, which is 2, minus 1, 2, 3, so negative 1. Okay, so overall negative. We have a positive on carbon 1, negative on carbon 4. And so these electrons are delocalized. One possible way that you could make a mistake here is after you drew this initial, so this is just a second possibility, just ignore these green, I guess, redraw this, get rid of these green arrows. So if we were operating under this second possibility, we could potentially make a mistake here and move electrons from the 1-2 bond to the 2-3 bond, following this up by trying to move this pi, this pi bond, over to the 4-5 carbon. Okay, so I've seen this happen a couple times, and it's a totally understandable mistake. But again, it's just going back to the same basic principle of carbon not being able to, accommodate more than 5 bonds. It's a very simple mistake to make, but it's also a very simple mistake to avoid. So again, if this is carbon 1, 2, 3, and 4, and 5 now, if we tried to actually put another bond on this 4 to 5 bond, what we'd end up having is we'll still have this hydrogen on 3, hydrogen on 4, and that looks okay. But thinking back to carbon 5 originally had 2 hydrogens on it. Okay, we know that because carbon 5 is neutral, so we have to have 4 covalent bonds on carbon 5. So now, since we haven't drawn any of those carbon-hydrogen bonds being broken, we have to remember they're still there. So for carbon 5 technically has 1, 2, 3, 4, 5 bonds to it, and so now obviously we're breaking the octet rule, so that's right out. Can't do that. Okay. All right. So moving on to the last question or last sub-question that I'm going to cover. There are a lot more in question 40, and I'd suggest you do them all. But for sub-question M, we have a slightly different setup than we played with before. We actually are messing around with a heteroatom, or a nitrogen, instead of just carbon. So in this case, you have to remember what we talked about in class, where nitrogen has this lone pair, and although this nitrogen does look like it's sp3 hybridized, we can go back to our rules for resonance, saying that we can actually move lone pairs as long as we don't skip over any sp3 hybridized carbons. And that's not what we're doing if we take this lone pair and try to play around with it. Okay, so it turns out that nitrogen can actually utilize this lone pair and push them as if it was in, as if they were in a p orbital. And so right now, technically, you would say that they were in an sp3 orbital, but it's close enough to a p to actually be able to overlap with the p orbital on carbon 1 and 2. Okay, so anyway, if that doesn't make any sense, it's no big deal. Just remember that you can actually move this around. And if you can visualize the p orbitals, that's fantastic. It actually makes things a lot easier for you if you can visualize p orbitals. But if not, it's not going to keep you from doing the problem. Okay, anyway, tangent. So we can use this lone pair and move them onto this nitrogen-carbon bond. But again, if we do that, we have to remember always and forever that we have this octet rule for carbon. So in this case, we have to prevent ourselves from breaking the octet rule, making a Texas carbon, by breaking this other pi bond. So going back to this mantra, if you make a bond, you have to break a bond. And that's, again, only assuming that you're going to break the octet rule. So if you're going to break the octet rule, if you make a bond, you have to break a bond. Okay, so let's go ahead and make a bond, and let's break a bond. Okay, so we made a bond, we've broken a bond, and now all we have to do is show the resulting structure. So let's make sure we get all of our carbons right. So we have 2 carbons to begin with, then we have a nitrogen, then we have 1, 2, 3 carbons total, 1, 2, 3 carbons total, and we made a new pi bond right here. Okay, and we have that hydrogen that we originally had, and nitrogen still has another hydrogen on it. And now this carbon 2 right here has a hydrogen as well as a lone pair. Okay, so now going back to, it looks like we have all of our bonds made and broken appropriately. Now we have to go back to making sure that we've done our charge calculation properly. So at this point, hopefully it looks, if you see a nitrogen with 4 bonds on it, it should look kind of funky. You should go ahead and convince yourself that this nitrogen has a positive charge on it by doing a formal charge calculation. So it's going to be 5 minus 1, 2, 3, 4. So valence for nitrogen is 5, and then we have 4 covalent bonds, so 5 minus 4 is plus. So nitrogen is going to have a positive charge, and so right when you find that, you should know there needs to be a negative charge somewhere, because overall this original molecule had a neutral overall charge, so that must mean that this resonance form also has a neutral overall charge somewhere. Okay, so obviously carbon 2 is giving itself away very easily by that lone pair, so if we do our formal charge calculation, it's going to be 4 minus 1, 2, 3, 4, 5, negative charge on carbon 2. Okay, so that's pretty much it. There are a lot of sub-questions for this. Go ahead and give them a go. If you have any questions, feel free to ask. Just remember that always double check your bond count, your covalent bond count. Always double check your charge. Always make sure you're not going to be skipping over any sp3 carbons. Okay, and if you do that, you'll be okay the majority of the time.